Good morning, everyone. This is a quick refresher on mesoscale precipitation bands and their forecasting. We have one out there this morning that's currently moving across the Raleigh and Wakefield CWA. Unfortunately, the KRAX radar is down, and as a result, we're not able to detect it terribly well over central North Carolina, but you can see the enhanced reflectivity on the order of about 5 to 10 miles wide, embedded within the larger scale 100 to 150 mile wide band of rain that's currently moving through the middle Atlantic states. And if we look a little closer into the depth of that band, that will be important when we start to look at diagnostics in just a minute. But notice that the band is sampled at about 5,000 feet, and then as we go up we start to lose it, and the top of it's generally about 8,000 feet there as we sample it there, mainly over Wakefield's CWA, although again it does extend back over Raleigh. And within that band, interestingly, the precipitation rates were locally enhanced, and they were on the order of about 1/10 of an inch an hour. But within the band itself, we had anywhere from 1/3 to 4/10 of an inch. Notice back toward Durham, there was 33/100ths there in an hour, and then when it moved over or that was Chapel Hill rather, and then when it moved over Raleigh-Durham, 37/100ths of an inch. And just here locally, in the last 10 or 15 minutes, you could really hear it hitting the windows and increasing in intensity. So indeed, the precipitation rates were enhanced. So if we look at why that precipitation band is there, then the telltale sign is strong phrenogenesis. Oftentimes, when it gets overrun by stronger QG forcing for ascent with an upper trough, for example. And this is 925 Pedersen phrenogenesis from the SPC meso page, and you can see very, very strong there, centered right near where the band is. And if we expand up to 850 millibars, as is typically the case, the frontal zone is sloped into the cold air, so that's why you see the 850 FGen max displaced slightly to the west of the 925. And we can look at the layer 1,000 to 925, for example, which is a little bit farther east because it's going down to 1,000 millibars up through 925. And then just for completeness, the 850 to 925 layer there. It's relatively shallow, though. If we go up to 700 millibars, for example, the layer averaged 850 to 7. Not a whole lot there, and that little contour over Virginia and then back toward western North Carolina is largely a result of the 850 FGen and not at 700. So again, it's very, very shallow FGen, but strong, and that's all occurring within the frontal zone, which last evening at 0Z was well sampled by the RAOB data. We've got 850 RAOBs here in the bottom left. You can see 4C at Nashville, 9C at Atlanta, 7 at Greensboro, 8 at Morehead City, and notice the trough axis in there with the westerly flow at Nashville and subtly to south-southwesterly over the Carolinas. In addition, if you look at the bottom left panel there, that's the 925 RAOB data. You can see 8 degrees at Nashville and then 10 at Greensboro, for example, and strong convergence there with the west-northwest flow and southerly flow. And again, that was at 0Z. We're now at almost 10Z this morning, but we can use VWP data from the regional radar imagery. And this is the 925 and 850 millibar layer VWP. And notice that the strong trough in that layer is indeed extending right across central North Carolina, coincident with where that precipitation band is and where the strong FGen was analyzed on the SPC mesoanalysis data. So a quick diagnostic, how would we forecast that? I put together a quick cross-section here, and if we go back, well, before we look at the cross-section, this is actually from old winter weather training from, 10 years ago, but you want to assess both the stability and the forcing, particularly QG, deep layer forcing for ascent, and then frontogenetical mesoscale forcing for ascent. And one of the things, there are all sorts of precipitation bands and pattern recognition, and while this isn't the classic characteristic northwest side of a low deformation band and mesoscale precipitation band, this is another somewhat more, atypical mesoscale precipitation band along a strong frontal zone as opposed to with a well-defined low. And notice that as your stability decreases, then the precipitation band tightens and intensifies, And that's what we're seeing out there this morning, so we must have some instability. Well, there are three types of instability. Typical static gravitational, which is conditional, which you would assess with thermodynamic, like surface-based CAPE. Of course, there's none of that. We're strongly stable. And if you look at the mu CAPE, not really a whole lot of most unstable CAPE, maybe 100 joule per kilogram contour there, but not a whole lot of gravitational or conditional instability. So it must be one of the other forms of instability, either inertial and or symmetric, and CSI, which is, we'll show is important in this case. So inertial stability, typically you can get low inertial stability on the southern or equatorward side of an upper level jet. And indeed, if we look at the position of the current upper level jet, it's off to the northwest, and as a result we have strong anticyclonic shear vorticity over North Carolina. So that's promoting low inertial stability, which is good for CSI banding, for example. And then in addition, we have the other type, symmetric instability, and we can assess that. There was an old method where you looked at the slope of potential temperature contours. There's a new, better method where you look at EPV-G star, and where it's 0, that favors CSI banding, but you have to make sure that there's no upright or gravitational instability there, which you would assess again with mu CAPE in that layer, and we'll take a quick look at that. So this is a cross-section, and that cross-section is cut basically from near Boone to the Cape Hatteras near the North Carolina Outer Banks, with central North Carolina and the center of the mesoscale band right in the middle of that cross-section. And this is RAP 13 model data here, and if we look, this is RH with omega in yellow, and ageostrophic vertical circulation, which is a result of basically imbalance in the atmosphere. And if we take off some of these contours, you can see the ageostrophic vertical circulation is favoring upward motion in a shallow layer between about the surface and 500 millibars, right within that mesoscale precipitation band. And the saturation in RH is relatively low, all centered below 500 millibars. And not surprisingly, that vertical ageostrophic circulation is also about a strong phronogenesis maximum that we just analyzed through both the observational data and model data, the subjective analysis on the SPC meso page. But there's your strong FGen signal, mostly below 850 millibars, which is consistent with what we've seen. And not surprisingly, that's why the mesoscale precipitation band and radar data only extended up to a few thousand feet above that FGen maximum, on the order of about 8,000 feet, which is what we saw just a few minutes ago. And so what we do, look for the FGen, which we have, and typically CSI bands or resultant mesoscale precipitation bands result when the EPV-G star, which is in this image here, is sub-zero within or just above the layer of phronogenetic forcing. And indeed, this color curve basically highlights, it turns the lighter colors right at 0. And if we overlay the associated contours, that's all sub-zero EPV-G star with a max of, gosh, about -9/10 there, just above the surface. And that maximum, or minimum, I guess, with the -0.9 EPV-G star is right within and above the layer of maximum phronogenesis, which is consistent with the diagnostics for CSI banding. And with time, that FGen max with the frontal zone is forecast to continue moving eastward and weaken with time. But indeed, there's your EPV-G star max, or minimum, again, resulting in the mesoscale precipitation band and the CSI band. So just a little quick presentation with the observational data and model data and the resultant impact of anywhere from 3 to 4/10 of an inch of enhanced precipitation embedded within a larger scale, lighter precipitation band.